Live from my dining room, it's Saturday night! Or whatever time and day you happen to be watching this. Anywho, today we're talking about center of mass, which is going to mark a fundamental shift in how we start treating and thinking about objects. So far, we've been employing the point model, in which we've taken any object that we can think of, a block, a person, an airplane, a platypus, and we condense all of its funny shapes down to a single point. Well, all along, I kind of glossed over this idea that that point was actually located at the object's center of mass. So whatever weird shape this object has, here's our platypus, by the way, we've sort of condensed all of that mass into a single point, and we ignored the shape of the actual object. Everything was at that point. But that point was located at the center of mass. You can think of the center of mass as the average location of an object's mass. It's a coordinate. It's where something is located. It's a special point related to the object. But this average is a weighted average, and it's weighted by how far a particular piece of mass is away from some reference point. So the average location of an object's mass weighted by the distance of the mass from some reference point. We're going to find that the center of mass is important because it's going to start letting us actually think about the shapes of objects. If I have a long rod like this, it's no longer a point, it is extended out in space. However, we want to be able to treat this object more easily. We don't have to worry about every inch of the object. We can still kind of use our point model, but instead we'll assume, first of all, that this rod is uniform density. That is, no piece of it is denser or less dense than the other piece. So it's a constant density all the way through, and that means that, each half of this object has the same mass. So we would expect for such an object, a uniform object, the center of mass would lie dead center. So uniform density, you can use symmetry to predict where that center of mass is going to be. We can say that, at this center of mass is where the force of gravity acts. If we were drawing a force diagram, we would label the gravity vector coming straight down, as usual, at the center of mass. We don't need to draw gravity vectors going all the way down. I mean, it is acting on each bit of those masses in reality, but on average, and as a good approximation, we can say, hey, gravity acts equally over here and equally over here. The rod is really going to behave as if gravity were acting directly at the center. So, force of gravity acts at the center of mass. That's important. It also this idea lets us explain why certain objects are more stable than others. Imagine we had this neat little sandcastle bit where this is, we'll say it's uniform density all the way through. It's a three-dimensional object. It's symmetric, so we would expect the center of mass to lie somewhere down this center line. But if we're thinking about vertically, because the object's wider at the top and narrower at the bottom, there's more mass up here. And so if this were a perfectly symmetric object, it would be at the center, but that more mass up there is going to shift the location of that center of mass higher up. So the center of mass is not at the center of this object because of the way that it's shaped. let's imagine that we're going to like pin down one of the corners. This is a little hinge over which the object can rotate. And then we start tipping it over. We're going to push it from one side and watch it rotate about that hinge. Now, as that happens, we'll see that if we keep that hinge where it is, oops, the center of mass ends up being located on the right side of that pivot point. So if I draw my force vector down, we're going to see that because this gravitational force is on the right side of the pivot point, that's going to cause this thing to continue moving to the right, and it's going to be more likely to topple over. So gravity on the right, and it will topple under its own weight. On weight, right. Gravity on right, object not stable. Now, if we flip this thing upside down, so that the wider base, or the wider part is now the base of the object, well, that center of mass is closer to the ground now. We can still try to tip this thing over, but what we see now is that as that happens, that center of mass is now located to the left of that pivot point. And so that will tend to make the object fall back down in its original orientation, making it more stable than the other way around. So the gravity vectors on the left of the pivot will restore its original position. So this lets us start thinking about how different objects may actually behave due to where that center of mass is located. What the center of mass also lets us do is allows us to think about systems of multiple objects. Can we treat that system of two or more objects as a single object located at its center of mass? That lets us kind of get the average behavior of the system more readily. And so we're going to look at systems of discrete objects. If I have something like a collision or two cars, these are moving at different velocities, v2, v1. This has mass 1. This has a different mass 2. Instead of thinking this about two objects moving, I can think about it as, a single object located at that center of mass. And we have a velocity of the center of mass moving, and that coordinate at the center of the mass might be changing in time, but I'm only tracking one object instead of two, which is nice sometimes. This is a common thing you'll do in astronomy, where you might have something like a binary star or a star and its planet, and you can look at like how that system moves through space by tracking the center of mass rather than having to worry about where each star is at any given point. You just care about where the system is on average. And that's useful. That's helpful. It reduces a lot of complicated calculations. So how do we calculate the center of mass of a bunch of different objects? It's an average. So the center of mass, it is a vector. And we can think of this as where is its x coordinate? The x center of mass. So x vector center of mass represents the actual vector as a 2D quantity. X without the little hat is the specific x coordinate of the center of mass. And then we have the y center of mass. Where vertically is that center of mass located? We have to calculate out each coordinate separately. So the x center of mass is going to be written as a sum. So I'm going to use fancy sigma notation here. We're going to take each little piece of mass. Each object will have its own mass. And we're going to multiply that mass by how far in the x direction that object is from some reference point. So we take the mass, we figure out how far it is from a reference, and then that will be that bit. And then we take the next object, and we multiply by how far that object is away from the reference point. And we add that to the mix. And we keep doing that for every object that we have. So it is an average. We need to divide now by the total mass of the system. So this is mass weighted by distance. This is mass. This is the total mass. Note, you can't just cancel out the sigma and the m. It doesn't work that way. These are a bunch of terms added together, so they will not nicely cancel out. So to calculate the center of mass, you need to know where each object is and how much each object weighs, and then you calculate these sums and divide. The y1 proceeds exactly the same, but you replace all the x's with y's. So let's do an example. Let's see how we can actually employ this formula to calculate where the center of mass with a system would be. So let's imagine here on my table, I've got an array of random objects. We're going to define, for sake of reference, that the center of my table is the origin, and we've split it into sort of 4 quadrants of where objects could be. I've marked out a little grid on my table so I can more easily measure where things are. And I have a 3 kilogram object at this point here, which is 1 object up, or 1 unit up and 2 units to the right. I'm going to place a 4 kilogram object 2 units to the left and 1 unit up. I'm going to place a 2 kilogram object exactly at the center of the table. And then right on the edge here, we're going to have 2 units down and 1 unit to the left, a 1 kilogram object. And the question is, where is the center of mass of all these objects together? If I wanted to condense these 4 objects strewn about the table, where they are, into a single position, that's what we'd be finding here. So we need to do this calculation for both the x and the y. So here's our x coordinate for the center of mass. We're going to take each object's mass and multiply it by how far it is along that coordinate. So my first object, the 3 kilogram object, 3 times it is 1, 2 units to the right. So we multiply that by x, 2. Well, now my 4 kilogram object is 4 kilograms, but this mass is over on the left, and so we need to put its coordinate as -2. It is a vector, and so direction matters. Something on the left of the origin needs to be negative, something on the right needs to be positive. So that's what we've accounted for here. Our 2 kilogram object is directly at the center, so we put its coordinate at 0. It does not contribute to the numerator, but it does contribute to the overall mass. So a really heavy object at the center might not shift the coordinate one way or the other, but it does kind of draw it in by weighting it down below. And then finally, our 1 kilogram object is 1 unit to the left, and we would do 1 times -1 divided by the total mass. We've got 3 and 4 is 7, 2 and 1 gets us all the way to 10. So we divide by the total mass down there. So we have 6 minus 8 is -2, minus another 1 gets us -3 over 10, or -0.3 units. We do the same thing for the y coordinate. Now we look at how far up or down our objects are. The 3 kilogram object is 1 unit up. The 4 kilogram object is also 1 unit up. Even though it's on the left side of the origin, it's still on the top half of the table, and so it is going to be weighted by a +1. The object at the origin still is at 0 in the y direction, and so it does not contribute to the numerator. But our other object, our 1 kilogram object, is 2 units down. And so that's our numerator. No matter whether we're doing x or y, the total mass is still just 10. So we write that in. So we got 3 plus 4 is 7, minus 2 is 5. This one works out to a nice ½ a unit. So we would express our center of mass vector as negative 0.3 in the x direction, 0.5 in the y direction. So it looks like it would lay over here in the x, negative 1/3, and then halfway up in the y direction. Our center of mass would be right there. So we condense all 4 of these objects into a single object located a little over in quadrant 2 here, the top left side of the table. So that lets us, again, treat a crazy system of many objects as just a single object for whatever purposes you seem to have. So you add up each mass multiplied by where it is along that specific axis, then you divide by the total mass. That's all there is to it. There's another quantity that we can calculate, is the center of mass velocity. We want to know that now that we've condensed our object into a single point, how fast is it moving together as a system? It's calculated the same way as our coordinate, except instead of weighting each mass by its position, we're going to weight it by how fast it's going. So we're going to have a sum of mi, the velocity of each object, divided by, again, the total mass. So we've weighted the masses by their velocities. And hey, what do these things on top look like? They look like momentum. So we're basically adding up the momentum of each object and we're dividing it by the total mass of the system. So this is sum of momentum of system. So that means if we're in a situation where momentum is conserved, this is a very important concept. If momentum is conserved, that is, if there are no external forces on the system, momentum is conserved, this numerator has to be the same no matter what. So that means that the total mass isn't changing, the total momentum isn't changing. If we're in a collision or something, momentum would be conserved. That means the center of mass velocity is a constant. So that means no matter how the object is moving, no matter how it collides, if we know what the center of mass velocity is doing before the collision, we automatically know what's happening after the collision. So let's imagine we have 2 equally matched vehicles. They're going to collide in a head-on collision. The 2 objects are moving in opposite directions. The center of mass velocity is 0. In other words, these 2 cars are on opposite ends of the origin line here. They're moving in at constant speeds, and so no matter how far away they are from the line, they're symmetric about it. The center of mass velocity is basically just sitting here waiting for the cars to crash. So they crash, bang, and now the 2 cars are sitting at rest in a mangled heap of scrap. The velocity of the system is 0, but that correlates with our idea that VCOM was 0 before, and VCOM is 0 after. The center of mass velocity was constant. And this is true, and this is a simple example to illustrate, but this is true in any collision where we would expect momentum to be conserved. Another way we can apply this is we can imagine, you're in the summer, you're rafting on a lake, and so we have a raft of mass m, and you are standing on one edge of the raft, and you also have mass m. So the center of mass of this system should be located somewhere in between. The center of mass of the log is here. The center of mass of the person is on the left edge of the log. So if we kind of find the average of those centers of mass, we would expect the center of mass to be kind of halfway between the left edge and the center. Now, this brave soul is going to walk from the left edge to the right edge of the raft. the center of mass velocity must stay constant. So if he's just sitting here on the stationary raft, the center of mass velocity was originally 0. That means if COM was 0, that means the center of mass cannot move. So as he moves to the other side of the raft, we're going to see that the raft has to move to the left to compensate. So what we end up with is he's going to move, his feet are going to exert an internal force on the surface of the raft, which is going to push it backwards as he proceeds to the other side. That means that the raft is going to move backwards such that if this person is now on this side here, the center of mass is there, and we've just kind of switched which side the center of mass of the system is on relative to the raft. It started out on the left, the person moves to the other side, but the raft moves back accordingly. And that means that, how far did the raft have to move? It had to shift basically half of its length. If this piece is now over here, the raft moved 1/2 of its length back in the other direction. So we were able to predict this by knowing that center of mass velocity had to be 0. So the center of mass of the system had to stay in place. Wherever that center of mass is, it is always going to be at this original location of where it was. So that's kind of a nice little logical analysis of how we can apply conservation of momentum and center of mass velocity being constant to the situation of a person moving on a raft. That'll do it.